Well, let's start. Well, so what's number one? 4? Yep. So PCA is try to maximize the variance. Like, so if you project to 4, you project to 4, you get like this data, right? Which is more variance than, let's say, this one. If you project here, you get this variance, right? Uh, so this is 4. What about 2? 2, 14. No. So well, the dimension of PCA, right? Uh, is either the rank of your coordinate matrix, right? So what's the size of your coordinate matrix? So coordinate matrix is compute from the uh you take all the training data, which is 15 by 15, right? You cross product. So you get you not cross product. Cross product, right? So you get a 15 by 15 matrix, right? So it's the size of the Fourier matrix, which is 15 by 15. But this metric might not be full rank, but this is the maximum possible rank you can have is 15 by 15, which is the size. But the rank of this matrix is also governed by how many training data you use. And the rank is governed by the training data minus 1. So in this case, it's 15. Mhm. All right, then the third one, what's the size of the gram? Yeah. What, can you speak louder? The maximum is 15 that you can have. The minimum is 0. You can choose to do nothing. You can go up to 15 eigenvectors because your matrix is only 15 by 15. You cannot have more rank than the size of the matrix. Right. Oh, you mean here? I see. I thought you mean here. It's min. Yeah, it's the minimum. Yeah. I thought it's like maximum, huh? Yeah, it's minimum. Yeah. For the third question, gram matrix. So the size of the gram matrix is the uh the number of training data by training data, which is 1,000 by 1,000 in this case. Right. That's all. That's all for PCA. While we're at PCA, yesterday I was looking at like the AI tutor logs, and there's a question about how do you find eigenvectors and eigenvalues. In the homework, we don't expect you to do that. We expect you to just use Python libraries, linear algebra Python library. So you don't have to like write code to to solve for eigenvalues or eigenvectors. Just use the libraries. All right. So today, right, and for the next three lectures, uh, we're going to talk about like deep learning. So today is like the basics. Next lecture is more advanced, and the last lecture is about generative AI. But before we go into like deep learning, we're going to talk a little bit about a simple review of machine learning concepts. Right. So let's say I have like this kind of data, right? Cat and dogs, and I want to classify them by using weight and heights as my features. Right. So in machine learning, we usually start with kind of model, right? And when we talk about model, we usually refer to some function, right? So a model is just some function that is okay. Maybe my model is this line here, and my model will predict something like, oh, if this function give some number that is higher than zero, I say it's a dog, right? And if this number is lower than zero, I say the cat. Right? So this is the line for the function. And this line where the decision flip, right, flip from cat to dog, we usually call it the decision boundary. And this is an example of like a kind of classifier we talked about before, which is logistic regression. Is a linear classifier that is, it's a line, a straight line, that you kind of learn what kind of function it is. But when we discuss like on like if you want to use lines as straight lines uh to classify between these two classes, you actually have a lot of choices that are possible. Right, these are valid choice for me to pick, right? And which one, right? Which one should we select, right? So this is where the people who train the model have to decide, right? What line should we prefer, right? Which line do we prefer? Which line should we pick, right? And we determine this by selecting, like picking an objective function or a loss function. We pick a loss function and we use this to select like the best one, right? So maybe my loss function or my objective function is I sum all my dog data points on this function, and I also sum all my cat data points on this function, and this one minus this one, I want to maximize it, right? I want to find the line that maximizes. right? So I might put each line like, oh, let's compute this line with this objective function. Maybe this one is 20. This line is 30. This line is 25, let's say. Right. So in this case, I will pick this line. Right. I will pick this line. Right. So the objective function determines which line I should use or should according to the training data. Right. So this is done on training. Right. And this function is quite arbitrary on what you can pick. It really depends on the objective of you as an engineer. Right. For example, I can say that, oh, actually, I prefer this blue line. I prefer this blue line because I only need one sensor, which is the height. Right. I only need the height to make a decision rather than use two sensors. Right. This one is cheaper. So I might prefer this blue solution, and I have to construct an objective function that will capture this. And we'll discuss more about like how do we construct an objective function that we prefer smaller features. Right. So, but this thing, right, this thing is done on the training data. So if my test data, right, is something like this, right? I forgot the kind of dog. What is this? Sausage thing. Dachshund, I think, right? Dachshund, maybe. Right, Dachshund. Here, right? It might be wrong for this blue line, right? Or maybe this thing, which I have no idea. We can separate this with a line. Yeah, we can separate this with a line. Yes, right. So how, right? So that's when we start to look into more sophisticated. We need a curve, right? We need more sophisticated classifiers now, right? So we need curve, right? But if you go too much, right, in the picking like the most sophisticated you can think of, you can overfit on your data, right? So this is something that you need to be always be aware of. Like if you go for a more complicated model, you might overfit, and if you go for a too simple model, you might underfit. Right. So this is like the pretty much the key concept of all machine learning methods. You have some data, you have some model, you pick a function, right? And then you pick the best kind of function in that class, right? But you can pick different kind of models, but be careful about overfitting, underfitting. So how do we know? How do we know that we're overfitting or we're underfitting, right? So a key number that I usually look at is the difference between training error and test error. So usually you're trained, right? You guys are always taught that, oh, okay, you should look at the test error, right? And you only look at the test error. But my advice is always look at your training error as well. That is like, oh, you put your training data to your model and see how much error you have, right? And the difference between the two will tell you whether you're like overfitting or like underfitting, or you're doing okay, right? This difference is very important. For example, I might have like an accuracy of on the training, right? On the training, I might have 90%, and my test is maybe 80. Right. So let's compare this. Usually this is more relative. Let's compare this with another model. Another model might have a training error of 95. Right. Let's call it green model. And this one is 75. Right. So like this has a difference of 10%. This has a difference of 20%. Right. So one thing that you can say is this, oh, okay, the green model has more overfitting than the blue model. Right. So this gap in difference is always very important because it's very tempting for you to just say, oh, my model is overfitting. So the result is not so good because it's overfitting. It's like a get out of jail free card that people just say this word, right? But actually, I wouldn't say so, right? So this just happened yesterday with one of uh, my master student. He said, "Oh, my model has an accuracy of 45," and he said, "Test accuracy." I say, "Oh, this is overfitting. It's bad." Right. He's trying to like reduce his overfitting, and I'm like, okay, can you tell me the training accuracy? And he say, oh, and he go check, and his training accuracy is 48. Right. I'm like, okay, so you just pass your training data to your model, just like how you check test error, right? You pass test data to your model. This is like, oh, use the training data pass to your model. Right. And sometimes it can be very bad like this one. And I told my student that, are you doing something wrong? Before just blaming overfitting, are you sure that this task makes sense? He's doing like X-ray image classification, and what he did is like he resized the image to be smaller so that he can pass this small image to the model, right? But he forgot to look at that. Oh, when you resize the image to be very small, it's very hard to see the detail, right? So this task is like useless. I mean, it's not set up properly. It's set up to fail. The task is set up to fail. So instead of like worrying about like, oh, I'm overfitting, right? Just be sure to look at the test. I mean the training, right? Whether, oh, if your training is bad, right, there's no chance for your test to do well, right? Always expect your test data to be worse, right? But how much worse depend on how much overfitting you're experiencing, right? And on the other hand, underfitting is, okay, if your test data is performing worse than like standard, right? Whatever standard you want to pick, either like a human expert or like a model that you're trying to beat, and something like that. All right, so now that we're talking about like this test and train, right? Let's review another concept, which is data splitting. So why do we need a test data in the first place? right? Why do we need test data? We want to estimate the performance of the model when we use this model on something, right? We create an app, right? We use this model on the real world, right? So we need a test as a proxy for when we are going to use this app. So how can we like get this test data, right? So a common way, right? A common way is, let's say you have a data set, right? And then you cut it, right? You cut it into some ratio, let's say 80-20, okay? Or like 90-10, or like 75-25. You can cut in any percentage you want. This is for practice only. Like people don't do this in the real world, right? This is more like for homework assignments. So I give you some data, you split it according to whatever I designate, right? People don't do this. So don't think too simple like this when you're like doing real tasks. But when you split, at least, right? When you split, at least perform what we call stratify splitting. That is split so that the data has similar distribution between the train and test. For example, if I have like a Titanic data, right? Titanic data, 80% of them dies, right? And 20% live, right? Lives. When I split it into two parts, right? I want the same 80-20 distribution in both, right? So this is called stratified splitting. And inside sklearn, there's these two functions that you can use to do so. Does that mean we use scikit-learn now? Pretty much, yeah. From this homework on, you're like, whatever, we're now in deep learning territory. Nowadays, you can just like wipe code without doing scikit-learn as well. But this splitting, right, of 80-20 or 90-10, what's the goal of this splitting? So one of the goal is that, you have enough data to train, right? Enough data to train and enough data to estimate performance. Right. This is fine in most cases, but sometimes you have a very small data set. For example, maybe 100 sample data set, right? If you split 80-20, you only have like 20 data points to test. So another way that people use for very small data sets is what we call leave one out splitting. So let's say you have 100 data points. You're going to say, okay, I have 99 here, 1 here. So this is my test set. But if you only estimate on one data point, it will be very bad, right? So what people do is, okay, they use this, train model 1, test it, right? Maybe they get correct answer. And then they take another 99, let's say, take this 99 and then this one here. So train model 2, test it on 1, and let's say, this is wrong, right? And do another split. Let's say like this. This split, train a model number 3, test it. Correct answer. Do this multiple times. Right? Do this multiple times. And then you average this number. Right? So now your accuracy is 67%. Right? So this is like to create an illusion of like a larger test set while keeping a large training data. Right? So this is one way. If you have very small data sets. Right? Why is this for small data sets only? Because you have to train a lot of models. Right? If you do this 10 times, you train 10 models. Right? Or like depending on how much like how accurate you want this test error estimate to be. Right? You can do this like 30 times, 50 times, or whatever. Right. So in general, right? In general, this kind of concept of like having multiple splits of training and tests, and then you average the results, right? Is called bootstrapping. Yeah, it's a technique in statistics that you do draw the same set of data, like draw samples from the same set of data multiple times. It's a statistic concept. So you randomly split, train a model, predict on the test, do it multiple times. That's how you get your estimate. Right. So this technique, when you do a full random shuffle. Every time you do a random shuffle to split into train and test. Another technique that people usually do to ensure that the test set is different for all times, right? If you do random shuffle, the test set might be overlapping, right? If you do full random shuffle. So sometimes people want all the test set to be non-overlapping. This is called cross-validation. So you have some data and you split it. So this is called threefold cross-validation. You split the data into 3 parts and then use 2 parts to train and test, use 2 parts to train and test, use 2 parts to train and test. And then you average the accuracy to get a number. Right, so this is how you train and test a model on some data, right? But actually, we have another thing in machine learning. It's called hyperparameters. So when we train our linear regression, right, we have like a sum of zeta times x plus sum of zeta times x, right? This thing is learned by loss function, right? This zeta we learn by the loss function. This is called parameter, right? This is called parameter. We got from the minimizing the loss function. On the other hand, hyperparameters are something we pick ourselves somehow, right? Somehow. So it's whether it's learned, right? The parameter is something that is learned, while hyperparameter is something that we pick by trial and error or something. For example, In linear regression, the parameters are the weights. The hyperparameter is like the loss, whether it's the mean square error or mean absolute error, the degree of the polynomial, the features used, right? These are choices that the engineer pick. Or k-means, right? K-means, the hyperparameter is the number of k you pick, while the centroid is learned, right? Or like the PCA, right? The number of eigenvectors to use is the hyperparameter. The eigenvectors is the parameter that we learn. Right. So since we have this hyperparameter, right, that we pick, we need a way to guide us on how to pick these things. Right? We need some way to guide us. So what happens then is that we're not going to split into just training and test. We're going to split it into training, validation set, and test set. So we're going to split into 3 parts. This part is used to guide our hyperparameter selection. Right? Guide our hyperparameter selection. You can think of this as like you're studying for entrance exam, let's say, right? The practice questions are the training data, and then you might have a mock exam. A mock exam is your validation set, right? So you're like, oh, using the mock exam, you try to like figure out your weakness, or like try to figure out the best strategy to do well in the real entrance exam, right? In the real exam is the test set, right? So you have 3 tests, 3 data sets for 3 different functions. So how do we do it then, right? When we have 3 sets, usually, so this is for large data. In a large data set, usually you will split the test set out, and from the training set, you might do a cross validation on the validation set. So you fix the test sets, and this test set is usually held by a different team. So this is in practice. If you work at a company, this is like a best practice. That is like the model developer is a different person than like a product owner, and the product owner is the one that verify your model. Because if you have access to this, if you have easy access to this test data, it's very tempting to like, oh, try to cheat, like, oh, let's look at let's try to peek a little bit on this test set, what I'm doing wrong, right? And you'll be like overfitting to the test set, right? So in industry, usually it's a good idea to always have like a different data set that the development team don't see. And you can do this if you have large data, because this test set will be large enough. This test set will be large enough so that you're fine with like having a fixed data set. But if your test set is not large enough, you might do what we call nested CV. So you like shuffle the test set as well to simulate a larger data set. But coming back to the setting, in this setting, let's say that you run this, right? You run this, and you run this, and you say, oh, according to my spread here, I find that, oh, okay, the best polynomial degree in my linear regression is 3. My cross validation accuracy is 80. My test accuracy is 75. Right? I do it again. I got the best degree is 2. Accuracy is 78. Test accuracy is 80. I do it again. Got a different number. Right? So if I average this, I got 80%. Right? This 80% give like an estimate of like, oh, okay, if we do it like this, right? Our procedure or our pipeline of training a model will guarantee us around 80% accuracy. Right? So this is how you might do it. But then there's a question of like, oh, now you have 1 model, 2 model, 3 model. Which model do you deploy? First one, second one, or third model? Which model do you deploy? Should we pick this one, test accuracy highest? Or should we pick this one, cross validation accuracy highest? Well, first is this is you cannot compare cross validation accuracy because this one is compute on here. This one is compute on here. This one is compute on here. So different cross validation accuracy is compute on different validation sets. So it's not a direct apple to apple comparison, right? So you might choose this one. Another technique that you might do, depending on the kind of models you train, is that you say, oh, okay, my best model in general is a degree 2 linear regression. So I will use this training data, the whole training data, to train a degree 2 model and use as my fourth model, and this fourth model is the one that I will use. So you're making full use of the data that you have. Okay, so back to like the spread, right? Like I said, this like spreading, blah blah blah, right, is for academia, right? For real world, first is in the real world, if you want to like create an app for something, right? The first thing that you need to do is create a test set. Right? Create a test set that hopefully represent real use case. Right. So the dev set here is another name for validation set. It's another name. I usually like to call it dev set because it's shorter, stand for development. So the dev and the test set should represent real usage, right? And then you can use like different kind of training data, whatever data you can find, you can use it, but as long as your depth and test set represent real usage, you're fine. Another thing that people usually don't talk about, but I think it's very important when you're embark on like a project is the size, right? So let's say you go work at a company and the company say, okay, I want you to build some, I don't know, uh, what's what's uh what's in the topic today? Like I can't think of anything besides like, or maybe like PM 2.5. Okay, PM 2.5 predictor, right? So your boss might ask like, oh, how much data do you need to collect, right? So how to think about like the data set size? You need to think about the objective of each data set. First, the validation set. The validation set is used to tune hyperparameters, right? So the validation set should be big enough to notice a difference between algorithms so that I can pick the best one, right? So if you care about like a 0.1% difference in your application, right? A 0.1% difference is matters to you, then you probably want at least like 1,000 data points for the validation set. Otherwise, you won't notice a difference of like 0.1, right? So that's how you select the size. For the test, right? It should be large enough to give you confidence when you deploy it. So it should like good coverage, right? Good coverage, like has enough diversity in your data, right? If you're, I'm not sure, like in statistics, you guys learn confidence interval. Confidence interval, yeah. So in statistics, we talk about like, oh, if we have this much data points, your confidence interval is plus minus something, right? The same thing. If you have a test set of this size, when you estimate your error, you actually have this plus minus something as well. So you can change your data set size according to how much this plus minus thing you want to have. Okay. So now to the main topic of today. And you realize that why I go over all these review topics or like some practical topics before we go to this lecture is because we're going to use it a lot. Because in deep learning, practicality is a big concern because we're going to deal with overfitting, underfitting, dealing with all these kind of things a lot. All right, so neural networks is a technology that is like probably 40, 50 years old by now, right? But it just got popular around 2011. This is where it started getting popular again in 2011. And at that time, people rebrand it to deep learning. So these two are actually the same thing, just a rebranding of like the same technology. And it actually has a big effect on machine learning in general. So here's a timeline of different years, right? Different years and different data sets. So you have OCR digits. So this is like an image, and you predict like this is number 0, this is number 1. So this is OCR. ASR is transcribing speech, right? So you speak something and the model output text, right? So each line represents a different machine learning task. And here you notice like a -1 and 0. So -1 here means that this is the starting point of the text, right? So when this task is first conceived, how good is the model? We just set it to -1. So notice every task start at -1, so that we can have them on the same axis. And here, this 0 is human performance. That is, if you ask a human to do the same thing, how good can he do? And notice that, well, first, so I say like deep learning is around here. So deep learning happens here, right, in around 2011, 2012. Notice how like here ASR go very slowly and then it jumps very quickly, right? So this show like how deep learning pretty much transform how how good the machine learning model is, right? Another thing is that nowadays it takes a short amount of time for a task to go from -1 to 0, right? Before it takes like here it's like 30 years. People work on like ASR for 30 years, but it's never as good as humans. But with deep learning, it's like very good, right? Nowadays, question answering is like take a year to be as good as human, right? I'm not sure if any of you guys went to like the OpenAI talk on Friday. I noticed one comment about, this is like an advertisement. So like in that talk, like they mentioned about like when they first launched the Codex app, the performance on coding is like 5%. 1 year later, it's now 46%. Right? It's a big jump in a very short time. Right? And I think as long as you know a way, you have like a setup, right? A data set, a benchmark, right? It takes nowadays it takes a very short time to beat a benchmark. So why does like deep learning has like this resurgence in popularity? Because I said like, deep learning has been here for a long time, right? It's because nowadays we have big data. Hard disk is cheap, right? Hard disk is cheap. Cloud storage is everywhere now, right? Dropbox happens around like 2010, 11, something like that. So that's when like people start having cloud storage. With that, we can have more data, right? And also, besides just more data, we have GPUs. So in like around 2009 also, NVIDIA there's NVIDIA CUDA. So CUDA is like a library that lets you program on the GPU easily. Before that, it's very hard, right? So because NVIDIA released this library, people start using GPUs to do their compute, right? And because of this, right, they're the first one that released this easy library. Right? A lot of the software is built on top of this CUDA library. This one is closed source, right? But everybody use it, and it's the only single thing that force people to still use NVIDIA hardware because of this library. Otherwise, people will try to ditch it because it's a lot more expensive than AMD, right? 3 times more expensive, right? That's why NVIDIA stocks is like very good, right? Because of this, just this one decision that they made like almost 20 years ago, right? Lays the foundation for their market dominance today. And with data, with compute, right? You can build bigger models. And it turns out that that's the only key ingredient in the success of neural network. Neural network only works when you have a very large model. And what's the difference between traditional machine learning and deep learning? So usually if you have a traditional model, right, you have a simple model, right? And you have sophisticated features, right? You can do feature selection, feature engineering. You might do some like manipulation of the features, PCA and things like that, right? So that you can use it to the simple model. On the other hand, if you use deep learning, you expect the model to do this step for you, right? But there's a caveat, that is you need lots of data. So pretty much like the difference between traditional and deep learning is that you're sacrificing human effort, right? The engineer effort to like trying to do feature engineering, feature selection, to like annotators effort. You hire people from like India, hire people from Africa to label data for you. Right. For example, the company Scale AI. Have anyone heard of it? Scale AI. It's a company that do data annotation for big tech. So they just like, oh, they receive data from big tech, and then they're like, oh, okay, this is a car, this is a tree, right? So they just hire like people in like third world countries, right? And Meta just bought them last year for a very expensive amount. All right, so this lecture, right, will be split into 2 parts. One is about the function. What does our function look like? Right. So we talk about the heart of machine learning, right? The heart of machine learning is first having the function, right? Then the second part talks about the loss and how do we minimize this? How do we prevent overfitting, right? Because deep learning models is going to be very big, right? Very big. very sophisticated. So it will be very easy to overfit. How do we deal with it? All right, so we're going to talk about like the most basic building block in deep learning, which is a neuron. A neuron. Here, a neuron, right, in the human brain. So neural networks has been invented like 40 years ago. So at that time, right, people have been dreaming of like, oh, I want to build AI. Right? I want to build something that is smart, right? 40 years ago, right? At that time, right, you need inspiration, right? You need inspiration like, oh, I want to build something smart. Maybe I should copy something, right? I copy something from nature that I know is the most smart in the world, which is humans, right? So people at that time try to like copy the human brain, right? So they look into neurons, right? And the neurons take in electric signals, right? Electric signals from other neurons, and then send some signals to the other neurons. So okay, if I want to do this, right? If I want to simulate this using a computer, I can turn this into equations that is, oh, let's take input from other neurons, right? And combine them somehow. So let's combine it like this. Sum of weight multiplied by the input plus some bias. So we call this the bias. This is the weight, right? So this is pretty much linear regression function, right? So this one neuron is a linear regression. But people found that at that time, people found that, oh, actually, the human brain is not linear. That is, if you put something in, the output from the human, the neuron does not scale linearly. Makes sense, right? Because if your neuron can scale everything linearly, it means that I can put in like 1,000 voltage and it will give out 1,000 voltage out, which is not possible in the physical world. Your brain will get fried, right? So it's not linear. So they will have this, what people call activation function, right? Because the neuron, right? Most of the neurons in the brain doesn't activate. And it will only activate when some condition is met, some stimuli happens. That's when you start activating, right? So that's why they call this activation function. Nowadays, people mostly call this nonlinearity. Nonlinearity. Just to convey that, oh, okay, this function is nonlinear. The neural network that only consists of this kind of neuron is called a fully connected network. Or sometimes people call it dense network. A side note, anyone know how many neurons are there in the human brain? There's a meme answer for this. I'm not sure if you guys are old enough. A famous prime minister once said, eight our country, Prayut. Prayut one says, oh, the human brain has 84,000 neurons. It's yeah, usually an estimate is like usually people usually estimate it to around like more than 10 millions. Uh, mm, it really depends on how you count, but yeah, it's a lot. Uh, so why do we need those neurons in the first place, right? So if we just think about what happens if we have one neuron, right? What happens if we have one neuron? A neuron, like I said, is just linear regression, right? So our decision boundary will be a linear line, like a line. When I start combining multiple neurons, when I start combining multiple neurons, my decision boundary becomes more complicated, right? Even more complicated. Right? So as I build this more sophisticated model, my decision boundary can accommodate more sophisticated data sets. But you need to be careful about overfitting. Right. Okay, as you create this model, right? People start naming, like they have some naming conventions. So they call like the input, they call it the input layer. The output, they call it the output layer. And anything in between, they call it hidden layer. Right. The middle part is hidden layer. And a layer is just this thing that is in parallel, right? So this is layer 1, layer 2, layer 3. And usually the input, we also scale it to be zero mean unit variance, just like in other machine learning model. But what does this mean, right? What does this mean mathematically? So let's think about this a little bit. So if I have one neuron, right? If I have one neuron, I have my input, right? Which I represent as a vector of this X is just a vector. This is one data point, right? This weights is another vector, right? So if I want to compute the output here, I can compute it as W dot with X plus the bias, right? So I can write it like this. If I have multiple samples, so this is one data point, one data point, one data point, one data point, I can compute them all in parallel, right? I can compute them all in parallel like this, that, oh, okay, compute it here, right? Here, compute everything in parallel using the same matrix notation. If I have two neurons, I have two set of weights. One is neuron 1, the other one is neuron 2, right? I have two bias, right? I can write it as a matrix multiply as well, right? So everything can be packed into a very compact representation of matrix multiply plus vector, right? So this is why NVIDIA is very rich because GPU is built for doing this. Matrix multiply plus a vector, right? They even have a special command for this in the GPU. Okay, so this is one layer, right? One layer. I can write, right, what's happening in my neural network as something like this. That is, oh, I have some X, I pass to some weights plus bias, pass to some nonlinearity, pass it to some weights, bias, pass it to some nonlinearity. Or I can write it as a equation like this. Right? Notice X pass to here, pass to here, pass to here, right? I can write it as an equation, or I can draw it as a picture, right? This representation, this pictorial representation, people call it computation graph, right? It represents how your model, right, is processing the inputs. And when you write code software to train like a neural network model, you're usually defining, you have to write some code that define what your computation graph look like. Okay, so let's talk a little bit about this nonlinearity as well. So there are three main nonlinearities that people usually use. One is sigmoid, or the logistic function, which is this blue line here. Blue line, it starts at 0 and at 1. There's this tan edge. Tan edge is this green line, start at -1 and at 1. And the last one, which is rectified linear unit, or ReLU. So this ReLU is 0 if negative, and y for x if positive. So this is very similar to like a half wave rectifier if you like study circuits, right? Anything that is negative, don't pass. Anything that is positive, just pass through. So these are the equations. Doesn't matter much. I think the important things is to remember like sigmoid 0 to 1, tan H is -1 to 1, and ReLU is non-negative. And most popular is ReLU, right? If you don't know what to use, just use ReLU. Right? Just use ReLU. Another layer that is important is the softmax. So currently, all of our neuron is like sum of W plus X. I mean, sum of W multiply X, right? Sum of W X, sum of W X, sum of W X, and I output something, right? Output something. Let's say that I want to do a three class classifier. So I want to classify between cat, dog, and mouse, right? So if my model is like this, my equation is like this, right? I can output like 5 here, minus 2.5 here, 73 here, right? My number can be all over the place, right? Which is very hard to interpret. So what people do to make these numbers easier to interpret is this thing called softmax layer. So the softmax layer turn all these numbers into probabilities. So for example, here I have these random numbers. If I pass through a softmax, I get probability out of it. Notice how the three sum to 1. Right. So this is easier to interpret, right? Oh, it's like, oh, I have 50% chance to be a mouse, rather than I have like score of 0.8. Right? It's easier to interpret. So this is a softmax layer. How does it work, right? How does it work? So it works by passing your numbers here, pass it through this function. So I can calculate the probability of it being cat by exponential of -5 divided by exponential of -0.5 plus exponential of 0.5 plus exponential of 0.8. And I get 0.14. I can do like P of dog, which is exponential of 0.05 divided by everything else. Right? And I get 0.37. Right? Why does this work? Right? First, these numbers will sum to 1 because I divide it. Right? I divide it so that it's always sum to 1. Another property for probabilities is probability has to be greater than 0. Right? And that's where the exponent is for, because the exponent is this, right? It's always non-negative, right? That's why I pass through an exponent. Another thing to notice is, oh, here, this is the highest, right? The highest number. The highest number gives us the highest probability. And the lowest here, give us the lowest. So what the softmax do is just rescale the number, right? But the ranking is the same. Right? The ranking is the same, but we just rescale it. So sometimes if you just want the model to answer like, oh, what's your best guess? Output me the maximum. You don't have to do this. You don't have to do this normalizing step. You just output this thing. If you don't care about the probability value, you just want the maximum, you can skip this part. So these numbers that we put to the softmax, people call it logits. There's a special name. It's called logits. All right, so that's our function, right? Our function is a bunch of matrix multiply and nonlinearity, and maybe at the end we put a softmax, right? Very simple construction, but imagine like you have 100 layers, right? This equation just keep going on for 100 times, right? This equation just go on and on and on and on and on 100 times. Okay, then how do we train such a thing, right? How do we train such a thing? So we need a loss function. So there are two main loss functions. One is cross entropy, which is for classification tests. The other is MSE, which is for regression. Right, so we cover the two main tasks. So let's look at the first one, cross entropy loss, or CE. So let's look at the image first. So I have some model, right? I have some model that predicts the class, and this has some softmax, right? Softmax layer. So it outputs a probability. Okay. And this data point has a ground truth. This is label data, right? So let's say, okay, the answer is class 2. So I will construct a vector, a one hot vector that is 0 everywhere except for this correct class. So if the correct class is 2, my y here is 1. Right? The location will become 1. The rest will be 0. Right? So that's the setup. So how do I compute it? I will pass it through this equation. For each data point, I will pass through this equation. So what is this? Is negative of 0 times log 0.3 plus 1 log 0.2 plus 0 log 0.5. So this is 0. So I'm only left with negative log 0.2. So this is my loss. That is, it will look at the probability of the correct answer, right? Probability of the correct answer, we only look at that. And what does this value look like? Right, so let's say that a log function, this is a log function, right? A negative log looks like this. Right, negative log of look like this. If I have a 0.2, I will have, let's say, high value. Right. If I have a probability of 0.9, right, 0.9, this will be a low loss. Right. So this function encourage the model to output high probability for the correct class. Right. If I output like 0.9, I will have a low loss. If I output 0.2, which is bad, right? Which is bad, I will have a high loss. So this loss will encourage the model to give high probability for the correct class. Some notes on cross entropy loss. So cross entropy loss treats all errors are equally bad. Any misprediction is equally bad. But in certain cases, your task might not have equally bad outcomes. For example, if I have like I don't know, like a fruit sorter, right? I need to sort fruits, and I sort into bins. Like, oh, this is a perfect coconut. This is a good coconut. This is a bad coconut, right? I sort fruits, right? And my ground truth of this coconut is a perfect coconut, right? My model A, predicts this. Model B predict this. If you calculate the cross entropy loss, what happened? Which one is better? This one will have minus log 0.5. This one also is minus log 0.5. So these two models are equally good. But if you look at the details, which one is better? Model B, because model B give a 40% probability on good, while model A give 40% probability on bad, right? And the correct answer is perfect, right? So you want to wait. So in this case, right, the different errors are not the same. So if you run into this kind of problems, there's this thing that you can look at, but we won't go into the details. Another problem is here, model A and model B, ground truth, which one has a better loss? This one has better loss because it puts 45 probability here. Right? The other one just put in 40 probability. But which model is correct? Model A will answer the first class because the first class has the highest probability. Model B will answer the second class. Right? So the model, this one will answer wrong. This one answer correctly. Right? But it has a worse loss. Right? So this is some potential pitfalls that you might encounter sometime, that you have a better loss, but your model is worse. Another pitfall for cross entropy that you should be aware of is, since the loss function try to encourage the model to like, oh, give high probability to correct answer, right? It encourage to give high probability. So if you train a deep learning model, it has a tendency to give high answers all the time, right? No matter what, whether it's whether it's correct or not, right? It always like, oh, I'm 99% sure, because the loss function encourage this behavior, right? It try to push towards high probability, right? So you can have an overconfidence model. Now you can, yeah, for example, ChatGPT. Right. You have uh it give actually, but for ChatGPT is a slightly different phenomena, but that's one intuition that you can get, like, oh, you get a very overconfident model because of cause therapy. Another loss for regression is mean square error. We won't go into much detail because we already talked about this in linear regression. Uh, just some extra things that is in mean square error. Right. We square. This is we sometimes people call it L2 loss. And there's this L1 version, which is absolute. Right. The absolute is called L1 loss. Uh, and we discussed this briefly already. That is, L1 is more robust to outliers, right? But L2 is easier to optimize. So some big brain people say, oh, okay, if these two has different strengths, why not combine them? They call this smooth L1, which is this graph. So near this point is like L2, and near this point is like L1. So the equation looks like this. And just like in cross entropy, if different errors have different penalty, for example, like overestimate is more damaging than underestimate and things like that. There are some solutions that are asymmetric. That is like, oh, you can pick like I want to penalize overestimation more than underestimate, right? You can go look at uh, this like blogs and things like that to learn more. Another another thing that people do in deep learning is regularization. So I mentioned how like, oh, in deep learning, our model is going to be very sophisticated. It's going to overfit a lot. Right? Overfit a lot. How do we reduce overfitting? In machine learning, we have this term called regularization. This is like a blanket term, for any techniques that help reduce overfitting. So it's like a very broad category term. And in deep learning, there are two main ways to do. One is called explicit. That is, we're going to change the loss function directly. Right? Since it's direct on what we change, we call it explicit. We change the loss. That is, we change the objective directly. Uh, the other one is implicit, which anything else. Anything else is like implicit. So there are two famous kind of regularization, L1 and L2. This is different from here. Here we say L1 and L2 loss is not the same as L1 and L2 regularization. So this is L2 loss, and this is L1 reg. This is L2 reg. Right. The 2 and 1 just means, oh, are you squaring? Are you doing absolute? Right. Notice like how L1 and L2 just means that are you squaring or you're absoluting, but the loss is a loss. The regularization is something else, right? But what this regularization? The regularization just sum all my weights together. Sum all my weights together, right? And why does this help, right? Why does this help? So let's look at an example. So let's say I have one training data point, right? One training data point. I have this X data point, and I have to answer 10. Right? I have to answer 10. And my model is just, right? So this is my model. Right? So if I only have one data point, and I have to make this model answer 10, how many solutions are there? A lot, right? You have 3 variables, but you only have 1 point. So these are examples of anything that will make this function answer 10. Right? Any of this is valid. And this will be the case in your deep learning model as well. Nowadays, the deep learning model has more weights than your data points. Right? So the model has multiple lines that you can use, right? Multiple lines that you can use. Just like in the start of the lecture, we talk about like different lines, right? Which one do we pick, right? Which one do we pick? That's where us, the engineers, decide by heuristics. All of this is heuristic. We just believe that it will be good, right? And we will test whether it will be good or not in the validation set, right? But at least these are heuristics, right? So what does the heuristic give us? Let's look at L1 regularization. Sum of the weights. If I sum the weights, I will get this, right? And I want to minimize this term. Where is it minimum? It's minimum at here, right? So if you use L1 regularization, you will select a solution where most of your weights will be 0. Right. So L1 do feature selection. That is, these features, they are less important than W1 because W1 multiplies by 3. So this one is more important. So it will only pick W1, the rest is 0. In the same way, I talk about like here, right? A model that is aligned, like just using one sensor, right? This is from using L1 regularization. If you use L1 regularization, you're more likely to get a model that use less features. What about L2? L2 here, right? Which one is the least? Is here or this one, right? So this is L2 regularization. What's special about L2? If you look at the numbers, you notice that L2, the weights, they are more closer together. They're closer together compared to like here, right? It's like 3, and then the next number is like 0.5. This one is 5, and then -1, right? Or here, this is 3.3, and then 0, right? But here, the L2 is like 2, 1, 0. The number are more bunched up, right? Are more bunched up. Why? Because we are squaring, right? We're squaring. So if I have a large number, it will be very large, right? When you square something. So you don't want a large number, right? And you can have some small number. You can have some small number because if you square a small number, you get something smaller. So it's fine to have a small number. That doesn't have to be 0. Right. So L2 spreads the number, right? Spreads out the number. And this is where like our heuristics come in, the talk about heuristics. So we believe that when we spread out things, it will be less risky. Just like when we buy stocks, right? Buy stocks, we usually diversify, right? So that when something explode, we won't be badly hurt, right? The same thing, right? Here we're encouraging the model to spread their hedge, right? To buy different things. Hopefully that this will be beneficial, right? This is like all hopes, no guarantee. But it tends to work well. It tends to work well. So that's the loss function, right? The loss function. So how do we optimize this, right? How do we optimize this? So we're going to have like a loss, right? This loss function is, let's say L2, right? L2 is this loss function is like a function of x and the weights, right? Which is y minus the function square, right? I want to minimize this, right? Minimize this with respect to theta, right? We talked about gradient descent before, right? What do we do in gradient descent? We differentiate, right? We differentiate this term. So we get like 2y minus blah, 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 and then minus f. Right? But what is this f? What is this f? F is, let me put this. F is this big equation here, right? Where I said, oh, there's this 100 of them, right? 100 of them, very large, right? How do we differentiate this? So what we differentiate is, oh, if let's say this is F, right? I'm going to differentiate this with respect to W1, let's say. How do I do this? So you keep doing chain rule, right? Keep doing chain rule until you hit W1, right? You keep doing chain rule. So you have like 100 chain rule, right? Good thing that you don't have to do this by hand, right? That's where I said, oh, we're not going to do like NumPy anymore. We're just going from this homework on, we're just going to use libraries because it will be easier. So in neural networks, we're going to use chain rule, lots of them to differentiate. And people call this algorithm of like differentiating this loss function using chain rule. They call it backpropagation. Okay, backpropagation. So in backpropagation, there's a forward pass and a backward pass. So what does it look like? All right. So let's say that this is my model. My model. This is my computation graph. The forward pass is the green letters. So I have some starting points. I have some data, some training data, and then I compute my my data through the network, right? Compute the output. So this is my prediction. Compute the loss, and then I do backward. So the backward is the red thing. So this is the backward. I compute the chain rule, and chain rule you go from outside in, right? So if you have like G S, right? When you forward, you go inside out. Backward, when you do chain rule, you chain rule outside in, right? That's why the direction is different, right? And here this thing can be done in code. If you write a code, it will look something like this. Don't worry too much about it. This is where the libraries will help you. But if you want to do it by hand, you have to write this, right? Doing all the chain rule, things like that. Okay, so let's look at a visualization that help you like visualize what's going on in a neural network. So this is a website called TensorFlow Playground. So you can select like, oh, add more layers, add more neurons. And this is a classification problem. And notice like this line here, there's like an orange and blue, right? So this is the decision boundary between orange and blue for the model, right? So these dots are the training data. Okay, the training data. So I can set the learning rate. I can set the regularization. I can set the activation function. So let's do 10H for now. So I start with a random model. So the model is what? There are weights, right? So this thing has a weight of 0.36. This is 0.9. This is 0.3. Right? So these are the connections between neurons. I have the weights here. Let's train one step of gradient descent. So I'm going to press this button, press boom. And if I press a lot, notice my decision boundary is changing, right? And my weight is changed. So this is 8.5. If I press a couple, this is now 97, right? So it keep changing. And there's a plot here. This plot is test loss and training loss. This is the start when let's so if I keep training here, so this is a new loss. So so it keeps going down, right? Going down, right? Going down, right? So this is what happens when you do gradient descent on a neural network, right? And the thing we talk about, like, oh, let's increase the learning rate to 0.3. It's a lot faster. Like I only press it 4 times, right? Here, now it's epoch 5, right? And I got this circle already. If I have like 0.03, my 0.03, I have to like press many times before I get a circle. And okay, here, 85. All right. If I have a very sophisticated data, here's a very sophisticated data, and I try to train the model. Notice the top is test, the bottom is train. What does this mean? Overfitting, right? It keeps diverging, right? As you train more and more, this will happen in a neural network. Right? This is very common in neural network. So you always have to monitor what's going on, right? But this one, notice like it's like wiggling. What is this? It usually means that your learning rate is too high. If it's like wiggling, it means like you're like jumping around too much. Right. So they're like now it's becoming unstable. Right. The learning rate is too high. So this is probably a bad thing already. Let's restart. But if you have like very sophisticated thing like this, what do? I need more neurons, right? I need more sophisticated models. So let's add more neurons. It will take some time. But hopefully you get the idea, right? Let's go back to the slides. You can play around on your own at home, right? To get some sense of what's going on. Another thing that people do in neural networks is that we're not doing gradient descent, the vanilla version. We're going to do some spatial gradient descent. So usually in deep learning, we will work with large data sets. So let's say we have 1 million data points. So we can pass this to a model, get the loss, do the backward pass, right? Do the backward pass and update the model, right? Update the model. But this update, you only do one step and you have to compute 1 million data points. This is very expensive. Why? You can think of like, let's say that you want to ask like what people think about the current government. Like you do a poll, right? You're not going to go ask everyone in Thailand, right? You're going to subset a small group of people to ask like, oh, what do you think about the government now? Right? So it's cheaper, right? So the same thing, right? You're going to just subset a piece of the data, compute the forward and backward. Select another piece, compute forward and backward. Select another piece, compute forward and backward, so that this process is more efficient. Right? So you do a polling, right? To estimate the gradient. You're not going to compute the gradient on the full data set, but you're going to estimate the gradient. So that's why they call it stochastic gradient descent, because you're randomizing your poll, right? And this small subset, the small subset is called mini batch. And you're going to keep doing this mini batch thing, right? So let's say that I have 1 million data points and my mini batch is a size of 100. I can do this 10,000 times, right? When I finish this 10,000 times, I call it one epoch. Right. So one epoch means that, oh, I finish the entire data set. And one mini batch means like a small piece that I sample out. Next, we're going to talk a little bit about the learning rate. We show a little bit before in the UI website that we just show that the learning rate, right, pretty much control how your model going to behave, right? We saw like, oh, sometimes it can be too slow, sometimes it can explode and become unstable, right? So this is a way, a number that you need to try a different sets, like multiple sets of value to see which one does the best, right? It's a kind of hyperparameter of your model. Right? It's the thing that you select. But this thing is very important to your performance. And ideally, we want large learning weight at the start, because, for example, in this example, right, you want to do large steps so that you can overcome this hill. Right? You want to do large steps so that you can go over this hill. And near the end, you want small steps near the end so that you can like look into finer details. Right? Small learning rate at the end. Right? So because of this, right, you have two different settings. At the start, something, at the end, something. Is a good strategy to, let's say, oh, this is like at the epoch 1. Right? Epoch 1 start with high learning rate. And let's say epoch 10 go with low learning rate. Right? This is called learning rate scheduling. So you schedule how the learning rate change over time. Right? And this is very important. It can give you like 3 to 4 extra accuracy, 3 to 4 like percent extra accuracy if you do this tapering of the learning rate, at least. Uh, First, does this look familiar to you guys? Yes, Taylor series expansion in calculus. In calculus. So what does this mean, right? It means, oh, if I have a function, I'm here at theta. I'm asking like, oh, if I change theta by delta theta, what is my value? Right? What is my value? So the Taylor series expansion say, oh, if you only look at the two terms here, it means that, oh, okay, I look at the gradient and I estimate the changes according to the gradient. Right? So this is what it means to use the first the first derivative, right? In an expansion, you're estimating the new point by using the first order gradients. What's the downside of this first order gradient? Let's say that your curve looks like this. So it go down and then it go up very quickly. The first order gradient points here, but the second order might points up. Right? So to do a good minimization, right? To do good optimization, sometimes you need to look at the second order gradient as well. But this second order gradient looks like this. It's a matrix. So the first order gradient is a vector. The second order is a matrix. The third order is like 3 dimensions. So for every extra order of gradient, you get an extra dimension. So it's very expensive. So in deep learning training, people just ignore this part. And they're like, they're betting on that, oh, if I only use the first order, I'm still fine. When can we use only the first order gradients? Anyone remember from Taylor series? When can we ignore the rest of the terms? When this difference is small. When your delta theta is very small. Why? If your delta is small, this go to 0. Right? So you can ignore all the higher orders expansion, right? So baked into gradient descent is that, oh, you cannot move a large step, right? So this is a curse, right? A curse that, oh, I want to train the model very quickly, but I can only move very small, because if I move large, my estimation won't be correct. But people who do deep learning, they're very good engineers. By very good engineers mean they try to ignore all the math and come up with like some heuristics to do anything that make numbers go up. So first trick that engineers do is what they call momentum. So momentum is like a heuristic that try to compensate for this, like this approximation. Like we want to move farther away, but we don't want to calculate the second order gradient. So what they do is they take inspiration from physics. What do we want? We want something like this, right? We want to go downhill without getting stuck here, right? We want to go downhill without getting stuck here. So what do we do? If we have like a rock will roll down and go down, right? Why can the rock go past this hill? Yeah, it has inertia, or like people call it momentum, keeping the momentum. So that's why they call this technique momentum. That is, oh, there's some inertia that we're moving in this direction. We're moving this way, right? We're moving this way. So even though this is like a very temporary bump, since before we were moving this way, we keep the momentum, we keep the inertia to go on, right? So in math, they do this. So they keep track of what they call a speed. What is the speed? The speed is moving average of gradient. So there's this gradient, and notice current one is the previous one as the gradient. So the gradient, this V here, is just a moving average of the gradient, right? So you're keeping track, like, oh, from the past, which direction I'm going, right? From the past, which direction I'm going, to keep going the same direction. So what I'm going is going the same direction. So instead of So before I say W equals W plus delta W, now I'm saying W equals W plus V. Or you can think of it as this, like, oh, the momentum telling me, the gradient tells me to go this way. The momentum tells me to go this way. What I'm going is the sum of the two. A modification of momentum is what we call Nesterov momentum. So before, so this is the old, when we compute the gradient, we compute it at W. We compute it at W. But we're going to move it according to V. So instead of computing at W, we compute it at W minus V to get a better estimate of the gradient. Right? You can think of it as like, oh, before we compute the gradient here, and we move a combination of the two. Right? But since we know that we're going to move this way anyway, right? We're going to move this green direction anyway. Why not compute the gradient here? Let's compute at this point. So this is W minus beta V T minus 1. So we compute the gradient at this point instead. So this is called Nesterov momentum. So this is a visualization. Let's look at this one. So regular SGD is this red line. Notice how it's still stuck at some saddle point. We call this the saddle point. While other techniques, momentum, Nesterov, momentum energy, Nesterov, like they come down already. Or this is another image. I noticed like this is SGD. SGD is very slow. The rest finished already. And like Nesterov takes shorter, right? Nesterov takes shorter time than just regular momentum. So momentum and Nesterov momentum are just examples of heuristics that engineers just put into the the optimization. There are other techniques. The main ones now is Adam and Adam W. These two are the main ones that people use now. And these two are pretty much interchangeable. So if you see one or the other, I wouldn't worry too much. You can pretty much they're the same. And I just leave it like that, right? Just use these two. If you want to like learn more about them, you can read this blogs and things like that. All right, to summarize about learning weights and optimizers. First is always do learning weight scheduling, right? High learning weight at start, lower over time. if you start seeing overfitting, right? If you start seeing overfitting, decrease the learning rate. Right? This is a simple way to reduce overfitting. If you see it's start overfit, just reduce learning rate. So this is just an illustration of what I mean, like the gap, right? The gap, if the training and the validation, small gap, low overfitting. If the gap is high, strong overfitting, you need to do something. Right. So you always monitor this difference between training and validation. Right? I think this is a very common mistake that that uh, that juniors or people who are not familiar with deep learning will fall into. That is like they only look at the test or the validation performance, but I think a key indicator is the test performance as well. Another thing to point out is that if you monitor this graph, right? This is an ideal version of the graph. In real life, you'll notice like very squiggly graph. So it's hard to say when exactly overfitting starts, and you have to look at the trend instead, right? Be very blurry, right? And I think modern visualization tools will have like a baked-in uh, moving average to help you visualize this loss curve. Another technique that you can use to reduce overfitting is what we call dropout. So dropout is a technique where you have some model, right? So this is a simple layer. You're going to add in another layer, and we call it dropout layer. And this dropout layer acts as like a gate that, oh, I can decide to close or open randomly, right? I can close or open randomly. And there's a rate that I can set. So let's say that if my rate is 0.33, it means that 1 or 3 neurons will get randomly closed. Right. So one sample might go in and this one is closed. Another sample might go in and this one is closed. I choose at random which one to close. And what happens if you choose to randomly close things? You can think of like a model is trying to like answer correctly, right? But in the middle, there's you who just decided like to trick it, right? Close random things. What will the model do? The model will start to send information using multiple neurons at the same time, because it won't know which one to close, right? Which one will be closed. So you will the model will send information in multiple ways. So it will spread out the weights, right? So it's also a regularization technique, but this one is implicit. You don't change the loss function, you just change the model, but the outcome is the same. You get a model that is more spread out. So here's an example of a model with dropout and without. So if you have without dropout, you go up, go up, go up, go up, right? So this is training epochs. As you, oops, as you train, you overfit, go up, overfit without dropout. If you have dropout, there's no overfitting. Your model is fine. All right, that's all for the theory part. We're going to go over some code next. But before we go over the code, anyone has questions? Cool. So let's go over the code, which is the homework. Homework 5, right? Homework 5 is a Python notebook. So if you download it as like a IPYNB. So if you just open it in my course view, you get like this dump of thing. Just save it as a IPython notebook and open it. Oops, wrong. Let me open the version for guys. Okay, so in the homework, you're going to play with this data. So this data is a satellite image, right? And this is from a single satellite, Himawari 2. In Himawari 2, there's 16 sensors. Think of it like 16 cameras, right? And these 3 images are 3 cameras at the same time, right? They look different because these spatial cameras look at different things, right? So they look slightly different. So oops, here, right? Yeah, I forgot to share. So let me explain the data set real quick. So you have satellite image of Thailand, right? And we're going to do the task of now casting. Right? You might heard of like forecasting. Forecasting is what? Predicting the weather in the future, right? Now casting is predicting the weather now. What's the point of predicting the weather now? Because you want to sit in the building or something. So actually there's a use for this. So usually how do we know how much rain it is raining? We have like base stations. We have some station across Thailand, around 200 of them across Thailand. And each of the station, they have like devices to like measure the rainfall, right? But we only have 200. There's so much space in Thailand, right? So that's where the nowcasting task come in. We want to predict, oh, how is the rain here? There's no station, but I want to predict it. Right? So that's the task of nowcasting. So we in our data, we're going to take the station, right? So the station is here. We take 5 by 5 pixel of the image. So this is a 5 by 5. And we have 3 cameras, right? 3 cameras. This image captures one rainfall amount. Let's say 3 millimeters. So this is our task, right? Given the satellite image, predict the rainfall in the middle. And since usually when we think about weather, there's like time lapse, right? We want to know like, oh, the cloud is moving this way, right? So we actually have timestamps. So this is like 8 a.m. There's a picture in 8:10, 8:20, right? And there's numbers here like 5, 2. So we have like a time index. So we have 5 time steps of this updates as well. So that is our data set. So coming back to the Colab, the first part of the Colab just say, okay, read data, right? And our data is 200,000 data points. Each of them has 5 time steps. Each of them has 5 by 5 grid. Each of them has 3 cameras, right? Time step, grid, camera. This is X, our input. Y, our output is 5 rainfall numbers for the 5 time steps. The same number of data points. Train validation test. We're going to turn this into a simpler data format. So we're going to turn it by splitting. We're going to split, okay, let's split the time step into different segments and turn this into one big vector. So this one big vector is 75 numbers. Why? Because it's 5 times 5. 5 times 5 is 25. Times 3 is 75. So this vector is 75 here. And output one number. So that's why our data set now becomes 1 million. Because before we have 200,000. 200,000 times 5 becomes 1 million. 1 million with 75 vector. And then we pass it through a standard scalar to turn it into zero mean unit variance here, just like in scikit-learn. But we're going to create it as like a data pipeline, right? So we pass it to a normalizer and just normalize all our data sets. And then we create what PyTorch call a data loader. So a data loader acts as the thing that will create the mini batch for us. So it has some data set and you will draw mini batch, right? The small things that we throw out, right? And here I say, okay, mini batch is 1,000. So I have 1 million data set. I draw 1,000 at a time. I shuffle it. This pin memory thing, pin memory is helps the code run faster. It will preload the data to a specific to a specific where is it? Preload oops, did I edit undo? It will preload our data to a specific place in memory and fix it there. So it will be, the code will be faster, but it will use more memory. So if your model, if your computer cannot run the code, try turning this off, and it might be able to run if you run out of memory. You set the loss to be MSE loss. PyTorch has some built-in loss functions that you can just use directly. And this one is also interesting. So in PyTorch, they have the concept called device. So device is the place where you do most of the computation. So usually device is a GPU. In this case, it's called CUDA. That is like, oh, we are using NVIDIA GPU. So it checks if, oh, the code checks if there's a CUDA library installed. If it's installed, it means we have NVIDIA GPU, right? And we're going to set the device to CUDA. That is, PyTorch will know that, oh, we will compute it in NVIDIA. If you don't have a gaming laptop and you run this code on your laptop, it will say, oh, this is not true. And it will set device to CPU. That is, this code will run on CPU. It will be slower, but for this homework, I think it will be around the same. GPU or CPU doesn't really matter, around the same time, because the model is quite small. But this is like good practice so that your code can run on a GPU machine or CPU machine. Just use the same code. Just have this check. All right, then we start doing the deep learning part. So this is where you define the computation graph. So our model, our first model going to look like this. We have 75 as input. We're going to have three layers. One output. Right. So we want to build something like this. So what does our code look like? Our code look like, first, we have to initialize our variable. So we initialize all our layers. So this is a function that initialize a linear layer or the sum wx plus b. That's why it's called linear layer. Sum wx plus b. It takes in, this first number is how many numbers are we putting it in? And how many numbers is it outputting? Or the number of neurons. So this one, right, this one is called FF1. So we say, okay, we're going to call this one FF1. It takes in 75 numbers. It outputting 200 numbers, which means it has 200 neurons because each neuron output one number. Right, so this is layer one. Right, and what next? The next one say, oh, FF2, linear, hidden size. So it's FF2 take in 200, output 200. FF3, 200, 200. And the last one, which we call out, is 201. Right. But this is only the layers. We haven't connect them. So in PyTorch, we're going to define a function called forward. And this forward describe how the data flows. So the data X go to FF1, go to Lelu, go to FF1, go to Lelu, we call the output HD1. HD1 go to FF2, go to Lelu, HD2. Right, going through this, right, and we abuse the same variable y, right? Oh, y goes to the layer out and output y. We use the same variable and reshape it so that it's the same the shape that PyTorch expect. And since we define our computation graph. So now it's just like in sklearn where we initialize the model here, initialize the class. This is so that we send the model to our GPU. So this is the code. Oh, okay, send to GPU. Pick the optimizer to be a dumb. use a scheduler. Our scheduler is called reduced learning rate on plateau, which is, what is a plateau? It's like going up and then stop going up, right? Something like that, right? So, it's like, your models start to overfit somewhat. You're going to reduce learning rates, just like we discussed. So there's like a built-in function to do it. And so that's the setup, right? The setup. Let's move down to here, the training. So in the training, we start with a for loop for the epoch. So we say, okay, we're going to train it for 10 epoch. These are for keeping the logs, logging things. This one is a flag that say, okay, my model is going to be in this mode. So certain layers in PyTorch behave differently between training and inference. For example, dropout in training works differently from inference mode. The randomness thing, the random turning off, only happens in training. In inference, you won't do that. You just keep everything open. So we're going to signal here that, okay, we're in training mode. In the training mode, we have this thing. This is the data loader of the training. That is, it's outputting the mini batch. So this is the for loop of the mini batch. We get some data of the mini batch, send it to GPU. We set the gradient computation, pass input to the model. So this is the forward pass. Calculate the loss, backward computation, update. That is like do the step, like update the weights and do the logging. So this is the training part. After the training, we're going to do validation. So we're going to signal the model, okay, we're in inference mode. We say, okay, we're not going to compute the gradient here because we're going to only evaluate the model. So no gradient. For loop over the validation data. Put data to GPU, compute the output, compute the loss, but we don't do backward here, right? Just compute the loss. Keep track of the loss, right? After we're done, we say, okay, scheduler step. This one is the reduced learning rate on plateau. So if we go up a little bit here, scheduler is this thing. Scheduler is the reduced learning rate on plateau. So this happens after we compute the validation set. Right, so we check overfitting, and if it's overfit, reduce learning rate. Right, so every loop, every epoch, we do this. Training data, validation data, check overfitting, next epoch. And here we have a code that check for the best model. As we train, we save the best model. Right, so it's like, is it the best? If it's the best, save model. Right, so that's the gist of PyTorch. there are some extra things that I skipped. So this one, this is a helper library that help you visualize your model. So it takes in the input. So this is the size of the mini batch, 1,000 data points. Each of them is 75 dimension. So we say, okay, let's input this into model. What do we get out? So we get out this. So this is like the overall give an output of 1,024 and 1. Notice it's the same as this thing. So this is the overall, which is this final thing. All right, and each of them, for each layer is 200, 200, 200. Another thing to point out is this thing, parlam. Parlam is the number of parameters in your model. So let's compute this real quick. So this layer, right? This layer has, each neuron has this, right? Each neuron has this equation. So how many of these do I have in one neuron? I have 75 input. So I have 75 W. I have 1 by S. So I have 76 weights per neuron. I have 200 of them, right? So total parlam is 200 times 76, which is 15200, 15200, which is here the same. So this is like just like a check that, oh, you're writing everything correctly, because it's very common when you write this that you make small mistakes. For example, I'm like, okay, you copy paste this thing to the next one, right? Let's say you have this, right? You're like, okay, let's make the next one. The next one is this, right? And you're like, okay, make this. You forget to change. You change this to 2, but you forget to change this one. So you make a mistake because you copy paste and then you modify the numbers a little bit, right? That's a very common thing that people do, and then they make mistakes, and then usually when your code has some bug, right, it will break. But in deep learning, most of the time, simple mistakes like this will still work, and it will give you some reasonable number. Let's say that, oh, if you do everything correctly, you get 80% accuracy. If you do a small mistake, you get 75. Right? And usually when you're like, oh, I get 75%, you usually think, oh, I'm probably correct. Right? It's very hard to debug. Right? So this like simple checks will help. Another thing that happens at the start of this notebook is a tool called weights and bias. I'm not sure if you encounter this in like data science. No, right? Probably not. So there's a website called WANDB. So WANDB is like a logbook, a free logbook that you can sign up. And when you do experiments, you can send the the log to this website, and it will keep track of your logs. So for example, let me show you this one. So in this project, I have two models. It will show me in like a dashboard like this. So it's very convenient when you like train, like some people train like 60 models. And they have like problems like keeping track of like all the models and things like that, right? Oh, what did I run last time? I forgot the number. If you log everything into this website, it's very easy to like look through. And like you can look at validation loss, training loss, right? So these two, so the red and the blue curve, what's the difference between the two? The only difference is this, the learning rate. Like the rate, I keep the learning rate the same. Keep learning rate the same. The blue, I reduce the learning rate as I'm overfitting. And notice the difference. If I reduce the learning rate, it doesn't overfit. It does better. If I keep the learning rate, it's bad. Right? So you can keep track of experiments. And if you use it with Colab, you're going to log in. I mean, you're going to install and log in. When you log in, it will ask for an API key, which if you sign up, you can generate an API key that you use it here. And when you're going to log, you're going to say, okay, init, name your project, and send it some information. So this is the config file that you use for your experiments. So here is my config. I set different things like, oh, learning rate, hidden size. So I can keep track of like, oh, this experiment, what do I do? Because in my WAN-DB, I can look at, oh, okay, this experiment, I use this kind of config. I get this training loss, validation loss. I can keep track of different models, right? So it's a very convenient tool and a good practice for you to keep track of things. Okay, that's all for today. This homework, if you train it, it will take around 20 to 30 minutes if you use the full data set. If you don't want to waste your time, maybe you can sample, like reduce the size instead of using the full 1 million, use like 200,000, and it will be a lot faster. All right, any questions or comments before we end today? All right, cool. That's it then.